So last class we looked at how a normal distribution can sometimes be used in order to approximate a discrete variable. Today we're going to continue with that, and we're going to add on the fact that sometimes a normal distribution can actually be used to approximate a binomial probability distribution. In order to do that, there are a couple conditions that have to be met. So the first one is that n times p has to be greater than 5. And remember, n stands for number of trials, and p is the probability of success. And then n times q also has to be greater than 5. That's the second condition, where q is the probability of failure. If those two conditions are met, then we can use the binomial distribution, and we can approximate it using a normal distribution. In order to do the normal distribution, we need a mu, and the way we find mu is we do n times p. And we need a standard deviation, and the way we find the standard deviation is we take the square root of n times p times q. So, if you did a binomial distribution, and if you ran the model a bunch of times over and over and over again, when we ran 5 trials, we would have had this blue shape. If you ran 20 trials, you would have had this red shape. And if you had run 50 trials, you would have this green shape. So hopefully you can see that the more trials you have, the closer and closer it's getting to that nice normal approximation curve. And that's why we're able to use the normal approximation in order to approximate for a binomial distribution. And it's this whole fact that we need enough trials. That's why we have these two conditions here. That's why n times p has to be greater than 5 and n times q has to be greater than 5. Because they've calculated that if that's true, then our model is going to be close enough to this bell curve in order to get a fairly accurate calculation. So we'll go through an example. The probability of tossing a head with a weighted coin is 0.3. If the coin is tossed 60 times, what is the probability that 10 or fewer heads are tossed? Okay, so this is a binomial distribution, right? Remember, we have the conditions for binomial. There has to be a probability of success, a p. Okay, in this case, there is. The probability of flipping heads is 0.3. There has to be a probability of failure, not flipping heads, 0.7. And there has to be a number of specific trials, and that is 60. Okay? And then we are finding a specific number of successes in that specific number of trials. So there's two ways that you could do this. Okay, solution 1 is that you could do it the unit 4 way, where you find 10 or fewer heads means there could be 0 heads, plus the probability that there is 1 head, plus the probability that there's 2 heads, all the way up to the probability that x equals 10. Okay. And then you would have to actually work that out. So for x equals 0, you would do 60 trials, choose 0, probability of success to the power of 0, probability of failure to the power of 60, and you would keep going and do that the 11 times. That's one way of doing it. Solution 2 is to use the normal approximation. Okay, so first we always need to do our check, and you should show the check. So you need to do n times p, and you need to calculate n times q. Okay, so 60 times 0.3, and 60 times 0.7. And when we calculate that, we get 18, which is greater than 5. So we're good. And we get 42, which is also greater than 5. So both conditions check out. Okay. As soon as both conditions check out, we can then start doing the normal approximation. So, in order to do this, we're going to need to calculate our mu, which remember we do the mean by finding n times p, which we already actually found up here. It was part of our check. It's 18. And you need to calculate the standard deviation. So we do the square root of n times p times q, which is the square root of 60 times 0.3 times 0.7. And we're going to round to 2 decimal places, let's say. So we get a standard deviation of 3.55. Now that you're done this step, you have the mean, you have the standard deviation. It becomes exactly like a question in the last lesson. Okay, we're trying to find the probability that x is less than or equal to 10. Okay. That's a discrete value, so we need to apply continuity correction. Okay, so all the numbers that round to 10 or below, that would be anything less than 10.5. Okay, so we're going to find our z-score for 10.5. And we're going to draw out our little diagram so that we're showing what we're finding here. So the z-score, we would have 10.5 minus 18 all over 3.55, and we get a z-score of negative 2.11. Okay, so we go to our z-score table, and we look that up, and we get 0.0174 as our answer. So, in this case, it's probably about roughly the same amount of work, maybe even a little less to do the solution two-way, but hopefully we can see if it said, what's the probability that there are less than 30 heads tossed? You'd have to go 0 all the way up to 30. It's going to be much shorter to do it the normal approximation way. Okay, and even in this case, it's probably still shorter to do it the normal approximation way than calculating all of those binomial distributions and adding them all up. So let's give the next one a try. What is the probability that exactly 20 heads are tossed? So we already have the mu and the standard deviation, so we don't need to recalculate those. And remember, our mu is 18, and our standard deviation is 3.55. Okay, we want exactly 20. So I'm going to just draw the little bar here. If we want it to round to 20, the two x values that we're going to use are going to be 19.5 and 20.5. So, probability that x equals 20 is going to be, with continuity correction, the probability that x is between 19.5 and 20.5. So we're going to do the probability that x is less than 20.5 minus the probability that x is less than 19.5. Okay, so take a minute, pause the video, find your two z-scores, and do the subtraction. So you hopefully got a z-score of 0.42 and a z-score of 0.70. And then you would look those two up in the tables, and you would find that you get 0.7580 for that second z-score and 0.6628 for the first z-score. Okay, and that gives you a probability of 0.0952. Okay. And you could have also done this using the binomial formula. Here's our last example. A bank found that 24% of its loans to new small businesses become delinquent. If 200 small businesses are selected randomly from the bank's files, what is the probability at least 60 of them are delinquent? So this is one of those cases where you would not want to do it the unit 4 way. Okay, because 60 out of 200, that's a lot of cases to calculate. So let's go through this. We need an N, we need a P, and we need a Q. So for N, there's 200. That's how many they're pulling. Being delinquent is considered to be a success. So that's 24%, or 0.24. And then our Q would be 1 minus 0.24, which is 0.76. Okay, so next we need to do our little check to make sure that we are actually able to do the binomial distribution, normal approximation of the binomial distribution. So we need to do N times P, so 200 times 0.24, which is 48, and that is greater than 5 by a long shot, and then we have to do N times Q. And that equals 152 because it's the remainder of them. That's greater than 5. So we are allowed to do our normal approximation. Okay, so second step is to find our mu, which we've already calculated as 48 since that's just N times P. And then we calculate our standard deviation. So we do N times P times Q. Okay, and if we round that to 2 decimal places, we get 6.04. And now it becomes, once again, exactly like the problems from last day. We're finding the probability at least 60 of them are delinquent, so that's x is greater than or equal to 60. And then we have to turn that into the continuity correction. Okay, so if it has to be greater than or equal to 60, we need to think about all the values that round to 60 and above. So that's going to be anything greater than 59.5. And then we'll do our little sketch. And once again, it's up to you whether you call the x 60 or 59.5. But somewhere we have an x and we're looking for it to be greater than that. And if we want it to be greater than, we're first going to have to find the probability of it being less than. And then we're going to have to subtract that from 1. Okay, so pause it, take a minute, find the z value and the probability. So if you calculate the z-score, we get a z-score of 1.90. And if we look that up in the table, that gives us 97.13%. And 1 minus that would give us 2.87%. Okay, so that means that 2.87% probability that at least 60 of the loans are delinquent. So that's not too bad of a probability. Okay. So if you guys have any questions at all, please email your teacher. Otherwise, good luck with the homework.